This is a production of Cornell University.
Okay, so here are the orders. Okay, and here are the major characteristics that sort of set that soil apart. Okay, what do we in fact look for to tell us that these are these features? Basically, we look for diagnostic characteristics. Okay, I'm looking for the four legs. I'm looking, well, think of it in evolutionary senses. I'm starting to look for the ear bone. Okay, I'm starting to look for basically mRNA. I'm looking for or hip placement or things like that. I'm looking for does this sound familiar to people? Hip placement, ear bones, stuff like that. Okay, these are diagnostic features of evolutionary history in biological systems. Okay, so I'm going to look at the same thing. I'm going to look at diagnostic features in the evolutionary history of soils, and we have a bunch of them. The first one, we basically sort of break them apart. We have what we call epipedons, and we have diagnostic subsurface horizons. Epipedons are those diagnostic features we find on the surface of the soil, and the subsurface ones are the ones we find subsurface, down below. Okay? There's a slew of them. Okay? This is a couple of them. They're called epipedons because they're over the pedon. They may include part of the B horizon. Remember, we're talking about horizons versus diagnostic horizons. Okay? There's a variety of them. Some of them are called anthropic. They're human modified. They're high in phosphorus. There's pelagic. There's human modified, but years of manuring. Okay? These are basically what they look like. So we have the molic, we have umbric, ochric, melanic, histic, and we also have, and not on this slide, but we also have this anthropic and the pelagic. Okay? But let's take a look at these five. Okay? These are the epipedons. These are the surface diagnostic features. Okay? We have a molic epipedon. That diagnostic feature that we're looking for is high base saturation, deep high base saturation. Hold on. Okay, does that make sense? Okay, if I have a molic epipedon, the clue is in the name as to what order this is. If I have a molic epipedon, I have a mollisoil. Andy. Base saturation is a measure, you could have low or high. Base saturation is a measure of how many bases, another way we can sort of think of it at this point, we can think of this as nutrients, as elements. How many bases are present on that soil, or on the particles, or being held by the particles of that soil. That's what base saturation is. So a high base saturation is generally a high nutrient soil, but it also could include high salts. So yeah, it would be high nutrients, but potentially it could be problematic. Low base saturation means low nutrients. Okay, does that make sense? Okay, so I have high organic matter, deep, and I have high base saturation. Diagnostic, the characteristic I'm looking for, whether it's the ear bone or whatever, in this case, it's a mollisoil. Okay? If I have low base saturation, an umbric epipedon, low base saturation could move into some of those altisoils. Okay, if I have an ochric, low base saturation, thin light. Any ideas? Thin light is really the operative term here. Well, potentially. I'm actually more thinking along the lines of insectisols, but it has that low base saturation. So, okay, we move into the melanic. The clue's right there. Melanic, dark, but not organic. Volcanic materials. Next one over, histic. Histosoils. Histic, tissue. Okay? The diagnostic feature I'm looking for is organic matter. How much organic matter is in there? Does that make sense? I'm looking for the ear bone, the hip. Go. No, the green is corresponding to the depth of that diagnostic feature. So molics tend to be deep. Umbrics actually tend to be deep as well. Ochric, less. Okay, melanic, someplace in here. Histic, very shallow. Well, it's being deposited on top. Yes, and it does correspond. I mean, ochric does not have a lot of organic matter. This has got the most organic matter, so it's the darkest. Does that sort of answer the question? Go.
So wait, the green from one diagnostic to the other isn't the same in each situation?
The green in this has probably got the most The green itself is sort of indicative of the organic matter that's in it.
Okay, so with debug, the green means organic matter, but with molic, that means...
Organic matter as well. No, that means organic matter as well.
Okay, so all green here is just the level of organic matter.
The green represents the intensity of organic matter. I mean, the intensity of the color basically means more accumulation of organic matter. Okay, the bracket basically means how deep this material is, but you can notice in some of these, like the umbric and the molic, you get down to this end, it's not as dark as up there. But this is the depth of that diagnostic horizon, the epipedon in this case. There's another question. Go. You, go.
Okay. The base saturation, does that come from organic matter then?
It could come from organic matter, but it also could come from the weathering. Okay, so in this case, there's not a lot of weathering and not a lot of organic matter. Okay, but I'm starting to see some sort of development in there. Okay, so low base. That doesn't mean that these soils are infertile. It just means it hasn't been weathered. Go.
What are the names represent? What do they represent?
Well, in some case, this is definitely associated strictly with a mole soil. This is directly associated strictly with an andosol. This is strictly a histosoil. But these guys can be multiple soils. Okay, we're going to look at a combination of these diagnostic horizons to tell us what type of soil. I.e., just because I have the ear bone doesn't necessarily mean I'm human. Okay, there's other organisms out there that have the ear bone. I might have the combination of the ear bone, the tooth, and the hip to be said, okay, that's a human. Does that make sense? Okay. All right. So these other diagnostic horizons, we call these diagnostic subsurface horizons. There's more of them. Okay. Soils that have oxic, candic, spodic, argillic, natric, and cambic horizons due to the amount of time they have been developed. These soils, these features are diagnostic due to their development, just like evolution of us. Okay? This is where soil genesis comes back in. Because these features represent differences in that stage of development, in their soil genesis, they are used to group the different soils together. All the soils that have candic horizon, you guys step over here. Everything that has oxic, you're here. Everything that has an argillic, you guys are here. Now that's not to say that there's an overlap on them. We basically are looking at the combinations to figure out what type of species you are or what kind of order you are. Does that make sense? Okay. There are a bunch of them. Okay? I'm going to go through a couple of them. Okay? The first one is an oxic horizon. And an oxic horizon is diagnostic for an oxo soil. In some cases, I just need one diagnostic feature, and that's what it is. If I have a histic epipedon, I've got a histosoil. If I have an oxic horizon, I've got an oxosoil. But that's not the case for all of them. Some of them you have to have the multiples. Okay. If I have a candic or an argillic horizon that has little sodium, potassium, calcium, or magnesium, it's an ultisoil. On the other hand, if I have an argillic or a candic or a natric horizon that has a lot of that stuff, it's an alpha soil. High base saturation, low base saturation. Does that make sense? Sort of that reinforce the high versus low base saturation? Okay, so let's look at some of these diagnostic features. And this is out of your book, but this is basically all of the features that we're looking for. This is the ear, the hip, the tooth. This is all these different features, okay, listed. And what we're going to do is we're basically going to break it in half. We'll look at the top half, and then we'll look at the bottom half. Right? So let's start at the top. Here's that recent material. If I have no significant accumulation, okay, and I have a light-colored horizon with some removal, we have an albic horizon. You guys have met albic horizons. What are they called? What is the diagnostic? What's the master horizon term for it? It's an E horizon. Okay, so I look for E horizons. I've got an albic. Okay. On the other hand, if I have weak development, structure, color development, we call it a cambic. What kind of horizon was that? A BW. Okay. So if I start having accumulations of silicate clays, okay, if it's a high activity clay versus a low activity clay. If it's a high activity clay and I have low salt content or low sodium content, it's an argillic. You guys have met this one. This is a BT. On the other hand, if I have low or a high salt content, it's a natric horizon. Clay accumulation but high sodium. On the other hand, I've got low activity clays with moderate weathering and abrupt surface boundaries. It's a candic horizon. If it's under extreme weathering, deep horizons, we call it an oxic. Oxic diagnostic for oxisols. You start seeing the combinations, how you throw these things together, you start getting your soils. All right. If we have an accumulation of sulfur minerals, we've got a sulfuric horizon, diagnostic horizon. If we're having an accumulation of organic matter, cool high altitude tropics, high organic matter, a sombric horizon. Acid weathering with iron and aluminum oxides, a spodec horizon. Clays between a plow layer in cultivated soils, an agric. Keep going. We're just going to go through the varieties here. If I have an accumulation of inorganic salts, and they're carbonates versus gypsum versus a mix. If they're carbonates and they are not cemented, we call it a calcic horizon. If they are cemented, we call it a petrocalcic. If instead of carbonates we're actually looking at gypsum and they're not cemented, we call it a gypsic. If they are cemented, we call it a petrogypsic. Do you guys get the flow? Am I beating a dead horse at this point? You guys, we'll finish it off with the salic. Go. Cemented is when they harden up, like a cemented feature, versus a soft material. Okay, so if I have accumulations of calcium material and it's not hard, we call it a calcic horizon. On the other hand, if it gets rock-like, we call it a petrocalcic. And I'll show you some pictures of this so you can see the difference. Okay, accumulation of salts, it's mixed, we call it a salic horizon. And I want to talk about these guys as well because you're going to meet this one this week. Okay, if I have cementation of layers that have not anything to do with salts, okay, and they are resistant to water and root penetration, it is cemented due to silica, basically creating a hard pan, we call it a durpan. If it's cemented due to other features, but it's dense in a brittle pan, fragipan. And I'll talk about, this is sort of nebulous at this point. There's a number of different theories as to how this forms, and we'll talk about those theories in the field. On the other hand, if I have a very hard pan that's due to an iron or manganese cementation, we call it a plasic. So we hold these things, we look at all of these in combination, we throw them in together. These are the diagnostic features that tell us what soils orders we're in. Okay? Question.
What's
Pan is literally what it sounds like. It's a horizontal sheet of material.
Would it be like the top?
If it's a hard pan, no, it could be in the soil someplace. Okay, so this plastic right here, this is basically formed when the plow goes over something again and again and again. It's a subsurface, very thin. It's a a hard pan. Yeah, some of you guys might have seen the initial formation of it. There was some platy structure right underneath where the AP boundary was with the BW. That was the beginning of this type of pan. It wasn't hard enough to be basically termed a plastic horizon, but that's how they form. Go.
Just judging from that, could you judge which one of the pans it would be? Or would you have to wait till it develops?
In this case, it's weak structural development, so it would actually be a BW, so it would be a cambic.
Okay.
Does that make sense? Because it's not a pan yet. It's not a hard pan yet.
I mean, could you judge which one it would become?
Probably it would come into the. See, this has got iron and manganese cementation, so I'm not sure I'd call it a plasic. It's definitely not going to be a fragipan. It's not. I don't know. I would be stepping off a slippery slope if I started making that. But I hear you, and I'd be like, nah. I'd probably end up going this way, but it's got that iron and manganese cementation, and it's not because of that. This is because we're compacting it. We're hitting it again and again and again. Go.
Can the plow pan cause like any type of cancer form? It just depends on what the soil is?
It has to do with what the soil conditions are. These pans are not forming because of a plow. These pans are forming because of other things. The plow might, in that case, actually might help it happen, but this is not a plow pan. This is a plastic pan. Classic plastic. Okay, does that feel good? Any more questions so far? Okay, so let's take a look. Okay, go.
So is the age of the pan same as other horizons, or is it?
In the case of the arc port, that pan is there only because of management. So those other horizons are definitely older than that pan. Those EBTs that we saw farther down, those have been going on those have been forming for the last 10, 13,000 years. That pan that we're seeing, that plow pan that we're seeing underneath the AP, that's formed because with the last 100 years. So that's actually kind of interesting because you can see that certain types of processes will produce features very quickly. And some processes will take a long time. It's going to take a long time before that arc port becomes an oxosoil. I mean, a really long time. But if it stays stable, it will form there ultimately, I don't know, 100,000, million years from now. But, okay? You feel comfortable with this? So let's actually take a look at some of what these features look like. Okay? This is a molic epipedon sitting on top of an argillic. You can see how they overlap each other. I got a BT1 and a BT2. I've got an AP, an A2, old BW basically, or E. Actually, I don't know what A2. I don't remember what A2 is. It's the old nomenclature. Okay? But basically, we're looking at the molic epipedon overlapping the argillic. Underneath it is a BK. Okay? This is diagnostic K. Carbonates. Okay? But basically what we're looking at here is the two diagnostic features. We put these features together. In this case, the argillic isn't that important for the order classification. It'll be for more refined classification. We have this molic epipedon. This is probably a mollisol. Does that make sense? Yeah? Okay. All right. So, you've seen this slide before. Okay? This slide is basically parent material. Now, I want to show you this slide. This is a slide that's out of your book. Okay? And they are definitely similar. Okay? There's similarities there if you look at the two of them. Flick it back and forth. This is the map of the soil orders. So these are the 12 soil orders mapped across the United States. Now that's not to say that everything in here is an ultisoil or everything up here is whatever. Okay? There's a lot of inclusions, but this is the general map of where these orders are. Now if you look at the parent material, the geology, you can definitely see if we look at this 7 right in here, we're basically looking at ultisols. Big swath of ultisols right down here. Okay? If we look at this top zone up here, frozen, those are gellisols. We're not going to see the geology on that one because we don't go that far up. But does that make sense? Okay, so we're looking at parent material is not necessarily directly related to what we see on the ground. It does indicate what we're going to see, though. So here's the orders. That's the distribution of them. How do we actually key them out? How do we actually classify them? And we have what's called the keys to soil taxonomy. And what we do is we literally ask specific questions that are diagnostic for that horizon. The very first one is gellisols. Now starting today and going over the next 2 lectures, we're basically going to go on a safari. We're going to go on a safari and we're going to look at these soils. Now you've heard me talk about what these are. I want to show you what they are, and then I want to reinforce what we talked about. Say, gellisols. Do you guys remember the diagnostic feature for gellisols are? Frost turning, cryoturbation. Okay? So where are they distributed? Those high elevations where the frost is, where the permafrost is. This is the United States. We're looking at Alaska. Okay, this is where they are. Okay? The question that we ask, sitting right up there on the top, we're going to ask you one simple question as to what that diagnostic feature is. We're looking for the ear bone or the hip placement. Okay? Soils that have, one, a permafrost within 1 meter of the soil surface, or gelic materials, that's the cryoturbation materials, within 100 centimeters of the soil surface, and permafrost within 2 meters of the soil surface. Fairly simple, right? The diagnostic feature that I'm looking for is ice. If I have it, I've got a whale. If I have 4 legs and fur and it barks and it licks you every morning, it's a puppy or a dog. Okay, does that make sense? That's what we're looking for here. What do these soils look like? We might actually have to kill another light. Sorry. These are what these soils look like. And this is where we're going to stop today on this rather cool picture.
This has been a production of Cornell University, on the web at cornell.edu.